Hello and good day to all of you. So, welcome to my online electrical engineering review and tutorial channel. And my name is Michael C. Pasis and I am from Mapua University under the School of EECE. Okay, today we will tackle a very interesting topic here under the power systems lesson, and this is power system analysis per unit. So per unit can be single phase or three-phase analysis. But before we do that, to those who are not subscribed yet on this channel, so you can do so by clicking rather the subscribe button that is located on the right side of this video. And if you feel that this lecture is have an application on your technical expertise, you can like or share it also with your friends. Okay, let us have our discussion for today, and we need to start with symbols. Okay. The symbols that we will use on the problem solving on this topic. Okay, first we have a symbol of a circle, which is an AC machine. Your AC machine can be a generator or a motor, which is represented by an independent source or a circle here. Then you have a transformer, okay, which is connected in series between links of a transmission line, generator or load, or vice versa, and it is represented by two coils. Now this is single phase without any windings, but if there's a winding connected, KY ground delta, you're considering a three-phase system. Also, we have a bus bar, which is a line, okay, here, and a node, which is represented by a point. Also, you have an air circuit breaker, which is a box type protection here, and an oil circuit breaker or OCB, which is like a hump. Please take note, these are protective devices, but it is not important on our analysis, especially when considering performance. But anyway, it represents there are protective devices on the system. Actually, there's some things here like relay. It's like a symbol of a letter Z, and another one, fuse, like a box with a double line, parallel line. Okay, if you have an open-ended symbols here, like an arrow sign, a square, or a triangle, that is your loads. And if you have a ground, we already usually use this during AC circuit analysis and DC analysis as well. Okay, now this is very important also in terms of the connections of your rotating machines and your transformers, which is Y grounded, and a delta connected. And this is very, very important when you go to sequence networks, which is another separate topic under the lesson of power systems, because the lesson of power systems is very broad. And if we go forward to the more enhanced topics like short circuits, fault calculations, we can make use of these symbols on the connection diagrams. Okay, let us have these symbols integrated so that we can have a single line diagram, which is our footprint, which is our plan. Okay, so a single line diagram is also called a one line diagram. Okay, this is the same. One line diagram or a single line diagram is a per phase representation. So it means when you say per phase representation, you're going back again to lesson number 4 in terms of power systems 1 in terms of balanced polyphase. So it means if you have a per phase analysis or per phase representation, you're considering your one line diagram as balanced and representing it at one phase of the system, such as we can say line A or phase A. So please take note, we use phase A as our main reference. It's either being on balance or on a balanced state. We usually use that on lesson number 4. Okay, you can go back to that video so that you can recall those things. And then if we have that power or per phase representation of that system, it also indicates important informations like voltage, okay, like the total power, MVA, the percentage reactances, okay, and the power of the loads. So these are very, very important details for analysis. Okay, now, if you have a single line diagram, and we already know that is a per phase representation, we can now integrate all of those things into one example here. So in this example, I forgot this is just an arbitrary example. Okay, I could say 1 plus J2 ohms on the transmission line 1. Okay, we can equal them up. Okay, this is just an example, arbitrary example. So it means I just assume some of the all of the values here, so that we can represent that. You can see here 2 generators, 2 transformers, 3 rather, and a bus that connects your loads and your sources. You have 2 transmission lines, an air circuit breaker, and another load here, which if this is load 1, I could say this is load 2. For example, I have here 10 MVA. Okay, you have 0.85 power factor lag. So in this case, you can see that you can have all of the important information here. And again, in order to solve this problem, you need to analyze, okay, that this is different from an AC circuit simply because you're considering 3-phase machines and AC machines here, especially transformers. How can you model a transformer? Okay, that will be our next topic. How can you compute, for example, whatever the current that is flowing at your generator? You need to have the per unit equivalent circuit first, which is represented as an AC circuit in per unit, and then you will use different kinds of techniques or AC analysis to get that IG1. So in that case, you already have an idea, okay, of what is the overall power system all about. So you need to have the most important part of a power system analysis, which is modeling of the parameters in per unit. Okay, so this is just an introductory. Then on our next lesson, on next slide, we will discuss single phase per unit analysis. Stay tuned. Hi and hello to all of you. So we will continue our discussion on per unit systems, and this is under the lesson of Power Systems 2, Power System Analysis. Okay, to have a recap what we have described from the last slide, we described the per unit system and the single line diagram. Now we will discuss comprehensively the per unit system and its corresponding formulas, and especially to the application on single phase systems. Okay, before anything else, we need to know what is a power system all about. We already describing the power system analysis and its application. So what is a power system in definition? That is a system that converts electrical energy and transports electrical energy. So it means it is a whole system that it has your generation, your transmission, distribution, and utilization, so that your electrical energy can come to you with reliability and sufficient power quality. So that is a power system, and power system is a big subject, which I think when we have the some lessons on advanced power systems, so we can include some of them: protection, operations, reliability, quality are some examples of it. Okay, now if you already know what is power system, then let us continue our modeling of the power system, which is the per unit system. We need to model a system wherein we can analyze what is going on our power system. So per unit system is a simplification solution which contains transformers. So what we have described from our last slide, that we have two buses and two generators, and then there are two transformers as well. So you have two transformers, you need to model them in such a way that it will become a per unit equivalent circuit. So our main goal here is to transform or to convert your single line diagram to its corresponding per unit equivalent circuit. So this per unit equivalent circuit is the so-called AC circuit. And from the AC circuit, we can now solve what are the parameters that we need or required on that single line diagram. So what is per unit system formula? So per unit is just actual all over the base. So it means that if you have a volts, ampere, ohms, and base is also volt, ampere, ohms, it will cancel definitely because you divide it. The per unit here is dimensionless. So no unit at all. So if you have the actual value, you just divide it, or actual is the given value, then you divide it by the base. So the bases can be computed in every region of the system. We will have that application later when we have our problem solving on the next lesson. Okay, now, in order to have your per unit analysis, your transformers must be an ideal transformer. So we will tackle AC transformers when we go to machines. That is a separate lesson. So what is a ideal transformer? So an ideal transformer is a transformer that is a lossless transformer. Also, the angles of your primary and secondary is unaffected, and thus a transformer which is 100% in efficiency. Since you have a lossless transformer, your output will be also equal to your input. So therefore, your efficiencies is 100%. Now, if this is the case, then your apparent powers and your complex power, apparent power and reactive power is also the same in terms of output and input. So thus, in our base computations, it is not surprising anymore that P base is equal to Q base equal to S base. And S base is always constant all throughout the system, which means it is the, okay, we will talk at this further when we go to the next slide, which is the forever value. Say forever value, you have a bigger system, 1000 buses, 120 buses, that value will always be the same because the input powers will be equal to the output powers because we use an ideal transformer. Okay, so we already have the fundamental there, okay, the first formula. Then single phase base formulas, you need to convert, or you need to have the base computations first, which is very important because to get per unit, you need to have the base values. Well, these formulas looks familiar, simply because these formulas here are just circuit analysis formulas, like Z is equal to V all over I in terms of the base, and then the admittance is the inverse of Z base. That's why it is I base over V base. And last but not the least, okay, is Z base is equal to V base squared all over S base. So definitely, these formulas already looks familiar to you from our past lessons, simply because we discuss circuits first and then polyphase, and then we encounter all of this on the fundamentals. Okay, so our next slide, okay, we will discuss the so-called change of base formula and the three-phase formulas as well. So please stay tuned.